Alright, so this is proving Snell's Law, which is the problem we tried to work in class today, but with little success. I worked on it later in the day and figured out how to do it. And just for the record, I am an idiot. It was easy. I just didn't do it right. So to remind you, this is a different diagram, but similar to what's in your books, of how Snell's Law works. Our diagram looks similar, but slightly different, and that's okay. The primary equation is t equals t1 plus t2, and the constraint equation is that q is equal to x plus q minus x. And I know that sounds redundant, but really what it's saying is that from here to here is equal to the same thing from here, or adding those two distances up equals the total distance, x distance between A and B. That's all it means. Now we do need to change the time into distance over velocity, which we had done in class. The catch is, and this is what we didn't do, we need to express the distance in terms of the Pythagorean theorem. So this allows us to introduce x into our primary equation along with h1 and h2, but h1 and h2, as we discussed in class, are actually constants and therefore aren't going to make much of a difference. So in this case, compared to how we tried it earlier, theta is actually allowed to change if we tried to use a sine theta or a cosine theta in our primary equation, which actually complicates the derivative, and this is something I didn't think out in class. To simplify matters, if we use the Pythagorean theorem, the height of A and the height of B are not going to change even if the point O right here in the middle moves either left or right. So since the height won't change with any change in x, then that is a much better choice of variable for this problem. So taking the first derivative of time with respect to x yields 1/2 times h1 squared plus x squared to the negative 1/2 power times 2x, because we have to do the chain rule, over v1, plus 1/2 times h2 squared plus q minus x squared to the negative 1/2 power, and we have to do the chain rule on this parentheses as well, so it's going to be times 2q minus x times negative 1, and that extra negative 1 comes from deriving or from differentiating the q minus x part. So the arrows to help you guide your pencil if you are writing this down, which I do recommend because I had to spread it out. There's so much to write down. So to summarize my chain rules, this is part of the first chain rule. This is part of the first chain rule of the second term, and this negative 1 is from the chain rule from there. Okay, so we actually had one chain rule inside of another one in this case. Now that I have the derivative taken, I can simplify all of my terms. So you can see that I haven't written down my 1/2 this time, and that's because the 1/2 cancels out with the 2 from the 2x. I moved my negative 1 up to the front, so I changed my plus sign to a minus sign between my two major terms. Again, I had a 1/2 cancel out with a 2. Now that it's been simplified, I can rearrange it to get where I'm actually intending to go. So by putting the 1/2 power back as a square root and putting the negative back in the denominator, I can rewrite it as x over square root h1 squared plus x squared times 1 over v1. And I can do a similar thing with the second term, with the q minus x over square root of h2 squared plus q minus x squared. And then, of course, times 1 over v2. Now I'm setting this up to substitute my d1 and d2 back into this equation. Now at this time you might wonder why I want to substitute d1 and d2 back into the equation. And it's so that I can put sine theta 1 and sine theta 2 into this derivative. So I'm going to pause the writing just for a minute. If you go back to the original diagram, which I hope you either have your copy from class or you copied down the diagram from the beginning of this video, you can go back and look and see that x is your opposite and d1 is your hypotenuse. So this is opposite over hypotenuse, which is sine. Likewise, you can see that q minus x is the opposite on the right-hand side, and d2 is the hypotenuse on the right-hand side. Therefore, this is opposite over hypotenuse, which makes sine of theta 2. Now that I have my derivative completely simplified down and I have introduced my sines back into the derivative, I can optimize it by setting the derivative equal to 0. From there, it's just a simple add sine theta 2 over v2 to both sides of the equation, and I have my final form of the proof. And there it is. So looking at my paper that I have this worked on beside me, it took 1, 2, 3, 4, 5, 6, 7 lines total. It took me 1 page top to bottom, but that's also including extra space so that I can read it. So to summarize what the actual process was, number 1, the primary equation was the total time, with t equals d over v subbed in. Number 2, the constraint equation was the total x distance between the 2 points, and we had to use the Pythagorean theorem to introduce the constraint into the primary equation, which is number 3. Use the Pythagorean theorem to put all of the time equation into terms of x, take the derivative, set the derivative equal to 0 to optimize, and then after you optimize it, your proof is effectively done. QED. Alright, that's it. Thank you for being patient with me and giving me a chance to solve this later. Hope that y'all have a good evening, and see y'all later.